Assalamualaikum entrepreneurs. I hope you're doing great conditions. My name is Faiz, and today I would like to share about my very fundamental study on the behavior of simple peripheral frequency drive (BACHELOR). And this project is under supervision of Mr. MOHAMMAD and Mr. Mustafa. This presentation is supposed to outline all these chapters from the reports, and at the end of this presentation, I will conclude and summarize all the findings and journey that I have followed. So right here is the project development which I have done for the past 8 months, and this for the technical aspect where I have done the publishing works, the welding, fabrications, and the software installation and analysis. So let me show you in short video demonstrations. Let's start. Assalamualaikum entrepreneurs. My name is Faiz, and this is creative of FY22. Right here, my project is the title study on the behavior of simple with variable described in depth. And this is the specification for simple parts, the variable is called the parts, and the variable is definite. So the moment I press the right button and set this part run at 1000 RPM and this VFD. So supposedly the RPM will be 1000 if I set from 950 to 950 and equals to 40. So let me demonstrate a little bit about this RPM. So let's say we are setting to 900 RPM. I'll press run in 1, 2, 3. So that's it for the demonstrations. Thank you for your time. From these short videos, mostly you will get the ideas of my projects, and I will briefly explain for my projects. So this is the general response of the fuel pumps, which is the project I use is the 6 model, and this is the engine where it's got the general response right here. And for the past few years, actually, this SIMS project, the SIMS fuel pump was detached from XT Kelantan, one of the Navy vessels, and located at the workshop B20 in Terminal right now. And it's retrofit into ICE engines, internal combustion engines. So this is the project model overview in 3D model that I have developed using the AutoCAD, and this will give a little bit specifications about the framework, which is the induction AC motor, the single parts, and the variable frequency drive, or also the Asree controller. So it is said that inconsistent RPM is mainly due to moderate malfunctions due to high amplitude oscillations. And having said that, it will cause fragile fluctuations and cause range of problems for the engine performance. So similarly for this project, actually the uneven rotating ratings is caused by alternate current supply, and therefore I take implementations and propose the controller to solve my projects. The first question is actually how does the SIMS pump is working, and I want to see how does RPM of inconsistent affecting the fuel delivery. And there was the second question is how fuel characteristics, velocity stream and pressure are simulated at different RPM. So my first objective is to refurbish the SIMS pumps by VFD mechanisms, or known as controller, to control the RPM for experimental use. And then the second objective is to analyze the fluid flow characteristic as working pressure discharge by using the CF techniques. In my cases, I use the N6 fluids for to run the emulation. And this is the literature matrix that I have listed out from my table of matrices. And I have divided into 3 sections, which is the performance, the control of the speed. Next one is the CFD itself. And from the literature metrics, I have summarized all these kind of the questions and the answers, and supposedly some of the research questions have been answered by this summary. My methodology incorporates two techniques of zero-to graph and parallel works, which is this is the general flowcharts, and I have employed the use of few softwares during the journey. And this is the process flowcharts, which is for execution in three stages. The first one is the field bus setup, where I do the refurbishment works, the weldings, and the wirings, and so on, the troubleshootings. And the second stage of developing the analysis software, and the last stage of using the Excel to analyze my data collected. This is the troubleshooting flowchart, which is I refer some of the manual of the root cause analysis for the motor wirings, the generator manuals, the similar, same like at the workshop in 20, and one is the kind of cylinder engine, which is called fault line 1. This is my design and wiring diagram that I've used AutoCAD to actually give insight of what is expected outcome at the end of the journey, and this have been presented during the FYP ones. Highlighting here is the software parameters that I have analyzed and point out all and give into this one slide, so that in order to proceed to next stages, this software parameters is first need to be taken, and then now we can proceed to the next step of simulation. The first one is geometric preparations by using SolidWorks software, and then extract into any sequence of step 2, where I will start the machine and solder setup. I include all these parameters into the setup, and actually these parameters taken from the analysis of journals of past research and the manuals from the analysis fluid manual books. And the last step is the post-processing, where I start take the animation and extract the data. For the solver setups, actually this is the interface of the system and the software. Right here, this is actually the in-cylinder chamber. We can compare with this one. Actually, this is the electrical pump, and this animation will supposedly give you an idea how does actually the fuel pump is operates. So as the camera is rotating, the moment it have the right angles, you will push up the plunger and the barrels. This plunger and the barrels, and this reciprocating motions will cause the delivery of the fuel into the system. And for the fuel pump unit system, actually there is two systems that emphasized in this project, which is the first MOHAMMAD system, which is also known as direct inline, and the second one is the common rail system. And right here, the strokes between the initial and the end is 10 millimeters, and there is the inner ports, and spill ports, and the two delivery valve, and right here is the plunger and the barrels. So this is the fuel pump unit design, and right here is shown the four workings, principle of suction, compressions, delivery, and expansions, and it's level out all these labelings for the operations. And supposedly, I find that this fuel pump unit design capable of supply around 4 to 20 megapascal. This is the simulation results and an example of the in-cylinder chamber. So right here, this is the chamber that I have previously mentioned, and the fuel is supplied from this port, and this is the spill port, and this is the delivery port. And this is during the plunger and barrel at 0 millimeter, which is the initial. And this is the column for velocity magnitudes, and this one is the column for the pressure, dynamic pressure values. For your information, my simulation is done at a range of 500 rpm to 3000 rpm with interval of 500. And presenting to you right here, this is the 500 rpm and 1000 rpm. And the below ones is the pressure and velocity magnitudes at 0 millimeter, and the up one is the 10 millimeter. Same goes with the 1000s. And we get 150, 2000, 5 and 3000. And from this simulation result, actually, we can calculate the data of pressure distributions and the velocity distributions. Presenting you, this is the range between 500 to 3000, the discharge free pressure and suction free pressure. And we can see right here, the suction free pressure is 0.6 and constant. This is because I set it as the constant value, and same goes to the suction free velocity 3.5. And this value actually is from one of the literature that really is quite similar, but the only difference they use the gasoline fuels, which is the different intensity, and me myself use the discharge and different density. So this is the discharge free pressure, and right here this is the graph for these pressure distributions. I will highlight to this line graph consideration of this blue one. Supposedly, if the given value of 6 megapascal at 1000 rpm, in my logic, at first, if we increase the RPM to 2000, so the pressure will be twice, so it will be 12 megapascal. But the actuality is not aligned with that, because as go deeper with this my projects, I found that it's got these complex equations and lots of considerations during the simulations. And presenting, this is the trend line of the discharge free pressure and the constant, which is the suction free pressure. And for the velocity stream, actually, from the discharge free velocity, you will get the fuel flow rates that flow into the tubings. The injector of conglomerate design is flow into the conglomerate. And to be noted that the fuel flow rate, the amount for this simulation is remain constant, but the rate are different as the RPM increases. First, conclusions from my findings, actually from simulations, we can see this graphic right here. The gradient shaft RPM is proportional to the pressure and velocity, whereby increasing the RPM because increase of pressure increase and the velocity increase. And same goes with the flow rates, increasing the gradient shaft RPM because increasing of flow rate, but the amount of resupply constant. But we know that again, this simulation is only for MOHAMMAD system, which is the direct line. So from the fuel pumps goes into the injector directly, and not for the conglomerate system, which is a lot more considerations in the system. And from the literature itself, increasing of the fuel pressure supply is actually will cause shortage pressures and fasting rates. And this is the animation I have found, and one researcher found that increasing the pressure, which is this is the pressure line, and increasing the pressure will cause the shortage emissions, and you can see the crank angles is a little bit yellower than before. And from the literature also, for the conglomerate, actually the fuel pressure are summed up in rate of multiple fuel pumps. And for the MOHAMMAD system, the discharge fuel pressure are directly supplied to the injector. And I can conclude that increasing the gradient speed of the RPM actually will cause increasing of the pressure discharge and resulting in shortage emissions and faster conveyance. The conclusion for my project, the first one, the working principle, cause and effect of conventions are discussed as mentioned before in the literature. The second one, the fuel pump is refurbished, basically BFD for experimental use. and the field flow characteristic is simulated and analyzed accordingly. And there is the significance of my study, which I am able to assess the uneven malfunctioning of compounds or uneven field delivery, and this is discussed in the literature summary, and this provides in-depth understanding of the relationship between the RPM of the driving shaft and its impact on the field delivery. And the next one, I am able to develop this one of CFD model and simulate the object radar will be used for the CFD community and the future works. And this is the future works that I recommend myself, which is the pump performance and the efficiency of the efficiency and automatic curves. I do have ability to this kind of future works because I limited to this one value that I doesn't have, which is the ratings of the VFD and the model. And the only way to get this is by using the method, which is the another method and the software. And this project, of course, magnetically used by the government for education settings. And it shows that VFD implementations validate the further practical solution to control the RPM for fuel system. And actually, for information, the use of AFD in the marine system on board ships for the generator is already used. Some of them also use the same approach, and it's true that this really works. However, of course, there is certain constraint that I have gone through during the project implementations, and I can say that my limitations of my projects. The first, the data itself. The data collection and data validation. The first one, I do not have the specific manuals from the manufacturer, but I do have manuals of maintenance and looking, but is sufficient enough to this kind of data. But if given such manual from the makers, the manufacturers, I believe that the data will be more accurate. And the data validations mostly if given a better setup for testing the bad engines and the special tools for to refurbish the fuel pump itself, it will give much more better data validations. And because the resource concern, which is lack of fundings, and it cost me quite a lot if I have to keep going on to get the interesting performance by getting the data from the fuel pump also. And that's it from me, and this is my view the graph that bring journals, and thank you.
Thank you, Faiz. So let me give us for hardware. Okay, so the refurbishment that you've done is to include or to attach BFD,
Yes.
to the fuel pump. Okay. Any modification beside that?
Actually, for the PFD and the motor, of course, there is something that which is the capacity of the motor. This is not actually not recommended to them, but in order to make a success, this is the only way to remove the capacitor. And I have found a few technical staff, and they just say,
Okay. For that, your first conclusion totally to assess malfunction of fuel pump. Okay. So is there any malfunction of fuel pump before you proceed with the testing?
actually, for the SIMS concept, I do not know whether the malfunctions are caused because I assume that it's caused by the AC motor, and at first the fuel pump, the pattern of the injector is said that is with the uneven spray patterns, and but I can assess how the uneven patterns because I do not have any experimental rate, but I think it is true because the AC is not.
So that means you have not done any specification on fuel pumps, right?
On injector. On the fuel pump, yes, but I have done the elements on. But for the fuel system, from the fuel pump on the injector, I do nothing for the injector specific.
So after you have attached BFD, okay. So you have done the simulation through CFD.
Yeah.
Okay. So is there any actual reading from your device related with your simulation? I mean, the change of pressure, the change of flow. Is there any reading that you taken from your hardware?
Okay. For instance, I want to note that there's a lot of considerations or comparisons, and at first the objective is not to compare the two values, but I only want to analyze using the CFD, and the answer for your specification, I can say.
So you just for this project, so you just indicate the pump and the flow or when your complete system equal to safety and simulate the data. Okay. So what can be done to your hardware about the TGA, for TGA to
Actually, for TGA, for this, I think it's definitely for education settings. I have this kind of specifications and so on, the wiring diagrams from initially that I've analyzed and found from my readings. And from the VFE itself, it can alter the hertz first around 40 to 60 hertz, and this space around basically a basic supply. The next one we can use basically RPM, which is can use unlimited RPM, but in real life it's not recommended to do so because of the heatings and so on. But I believe that when doing this kind of settings will give the student, if they try this, they will give students the ideas of how actually the first the hertz play around with the RPMs, or maybe the RPM itself, the RPM settings, set to 1000, 2000s. And the last one is the top. The top is one of because in the VFD. It's have the settings just in the buttons. Can you show me your video production of your project? Here's that. Assalamualaikum warahmatullahi wabarakatuh. My name is Faiz and this is PhD of 2022. Right now, my project is entitled
so that's the BFD. That's all. Okay. So where can student can find the change of pressure? Where can student learn the effect of the BFD, the control of the behavior of RPM?
so actually this is the VFD, and I say that not only in this settings because there's some mechanics. But to answer your question about see the pressure discharge, actually they could not see until further refurbishments on the injector is done. And my project is only limited to these fuel pumps and this removal, but restricted to this the supply from the fuel tanks and the injector. So they cannot see yet these changes of the atomization of the gender, but they only can see the regulations of the RPM operation by changing the settings.
So they can just see the changes of RPM.
Yes.
Okay. So there is no indicator for flow meter, pressure, flow meter,
And velocity.
and
Pressure and velocity.
pressure and velocity.
Yeah. The right here is a pressure gauge, but the pressure gauge is more complex. It's because even if previously it's okay, but if inaccurate means.
So why you need to do this hardware? Since your project is done for simulation.
Actually, it's in the equations, and this question have been asked by the state and the state. But I would like to share a story because actually I did the similar approach of these problems into the same. Initially, I get the ideas from this paper, this the wiring is netted cables. I start from scratch from the paper. Then I get the idea to invest in the same. So I believe that implementing the technical skills will actually give me experience and more. And yes, it actually like between two FYPs and there is no communication.
Last question. For actual controlling of RPM, okay, what is the mechanism to control the RPM?
By means, the mechanism.
Yes, besides using BFD.
Oh, okay. Actually, maybe there's two different versions. The first one, the mechanism of BFD. Straight the BFD, they got the diode rectifier. This change the SCDC, and then we tune these changes of hertz or maybe RPMs. We make this one, these phases, and again from DC to AC, we will use the inverter. So that's how, in simplest way, that's using this BFD. And the question you are saying about either way to control RPM. Actually, there are four methods to control RPM. The first one is BFD itself, which is a good approach. The second one is VSD, variable speed drive. This have the same mechanism, but it's actually in a custom made from manufacturer, and it is really hard to find in short of time. I've find it around from December until January submission, but I cannot find the VSD, and I only have VFD. And the third one is the dimmer. Actually, the dimmer is one in the intensity of the voltage. Just let's say the dimmer control the intensity of the light. Change the potentiometer because they restrict the voltage by the capacitor and so on. But the thing is, it's not applicable in real life works because the dimmer will cause this motor, the windings, there is a stator and motor, the windings overheating and so on for the long term, and this is really not recommendable during my research. And the last one is using one kind of Arduino, like the same use. But the problem with Arduino is usually is for only to develop a kind of prototypes. It will incur more costs for me, and also to find Arduino to support 1.8 kilowatt rated is quite, it will be costly for me. And the additions I need to set up from the scratch of the coding, so it will be the technical reform.
Yes, basically, I just want to ask, for the actual case, okay, for example, if we run to full throttle, is there an opportunity to control the RPM?
Yes. Yes. Yeah, it's
by additional device.
oh, but for system of engine, yes.
Full throttle. Is there any possibility that we can control that again?
Yes, and yes, the answer is yes, of course. So the first one is called engine control module. For common system right now is have the kind of sensors. That's the simplest way. We push the throttle of the engines. It's ECM, send the signal to the serial pumps, and it's called the chemical and so on, and will give increase the RPMs. And also it's also affected by the government also. The government will increase the load and the torque, but that's for common modern engine. But this is the traditional engine, which is that doesn't have ECM, the solenoid valve and the sensors, but they use only by timing device and this the camshaft. And the only way to control the timing device is by push this throttle.
So I think check the pocket lah. Kan tekan minyak dia dan ada possibility kita kontrol RPM sebab kita tekan minyak RPM kan. Kan satu juga lah. Okay. So kita full throttle dia sama kita pakai full throttle. Okay. So for current method or current system. So soalan saya adalah so ada possibility untuk kita control RPM. Once kita dah set full throttle, itu soalan saya.
Okay.